Good morning, guys. Good afternoon, good evening. So, we want to show by mathematical induction. We want to show that this side is equal to this side for n element of natural number. How is the video blur? Okay. I told us yesterday, mathematical induction is a powerful tool and yet simple to test that a mathematical statement is true. You cannot be checking if the mathematical statement is true case by case. We have infinite number to test. So we cannot be testing all those numbers. We don't have time. And even though we have time, it's not possible because we have infinite number. So mathematical induction is how to know that the statement is true for any condition given to us. Are we together? That the statement is true without testing all those cases one by one. Now, now the base case, you have to check if it is true for n equals to 1. If you love fun, if you love math, if you want to enjoy, you can test if it's true for n equals to 2. Now, if you want to, on the left side, this one represents summation of the first term. Summation of the first term. If I'm testing for 2, it represents summation of the first two terms. If I'm testing if n equals to 3, it represents summation of the first 3 terms. I'm going to add the first 3 terms. If n is 4, I'm going to add the first 4 terms, even though it's not there, but I'm just explaining. If n is 5, I'm going to add all the first 5 terms on the left hand side. But on the right hand side, the meaning of this n on the right hand side is that wherever I see n, I'm going to put 1. If my n is 2, wherever I see n, I'm going to put 2. If my n is 3, wherever I see n, I'm going to put 3. But on this side, if n is 1, I'm going to pick the first term. If n is 2, I'm going to pick the first 2 terms and add them. If n is 3, I'm going to pick the first 3 terms and add them. So that's that for that. Now, so sorry, I'm coming. Now testing for n equals to 1. Now, pick the first term on the other side. So on this side, substitute 1 for n. N into 2n plus 1. So here I'm having 3 equals to 1, 2 plus 1. Therefore, I'm having 3 equals to 3. Like, show that it's true for n equals to 1. Now that 3 equals to 3, that means both sides they are true for n equals to 1. Therefore, the statement is true. It is true for n equals to 1. If you want to try to, you can try it. Let me just add 2. But after the base case, after n equals to 1, you can just move to your induction hypothesis. Show that it's true. Show that it's true for n equals to 2. So that is, I'm going to pick the first 2 terms here. 3 plus 7 equals to. So wherever I see n here, I'm going to put 2. 2 into 2 plus 1. 3 plus 7, 10 equals to 2. 2 times 2, 4 plus 1. So I'm having 10 equals to 2 times 5. So I'm having 10 equals to 10. Therefore, it is true for n equals to 2. Are we together? But you cannot be trying all those numbers. Show is true for 3, show is true. No. But you are going to assume. That's what we call our induction hypothesis. Induction hypothesis. Whereby you are going to assume it is true for n equals to k. You are going to assume that it is true for n equals to k. This k can be a very large number. No, we have a lot of number here. The fact that you are saying dot, there are many numbers here, of which we cannot be testing one by one. So we just assume that it's true for a particular number, which is k. We don't know that k. We assume it. So now, whenever you are doing n equals to k, write everything. That means you are doing summation of the first k terms. That k can be 100, can be anything. So you just take everything here. Whenever you are doing k, you take everything here. Because you don't know what k is, so you are taking everything here. You are adding everything there. 3 plus 7 plus 11 plus plus 4. But this time you are not writing this n. You are putting k. Do you get? You know our n equals to k now. Whenever your n equals to k, write everything on the left hand side and replace n with k too. You are still adding everything on the left hand side. Not everything. When n is 1, you only pick 1. When n is 2, you only pick 2. If n is 3, you only pick 3 and add. But if n is k, you pick everything and add them. You write everything the way it is in the question, but you now put k for n equals to. Now, the right hand side is n 2n plus 1. But now substitute k. We have been doing substitution for the right hand side. K 2k plus 1. So you cannot solve this one because of this dot dot dot. There is nothing you want to solve. This dot dot dot, there are missing terms there. There is no how to proceed with this. So you are done with your induction hypothesis. But yet you can't conclude that the statement is true for all natural numbers of n. Now, how do you conclude? If it is true for n equals to k, then it is also true for n equals to k plus 1. That is, assuming my k is 500. So if it is true for 500, then it should be true for 501. Do you understand? So that k is just an assumption that it can represent any natural number. So if it's true for that any natural number, then it is also true for the next number after the natural number we pick. So if you can show that one, that means it's true for all natural number. So when you have done your k, then if it is true for n equals to k, then it is true for n equals to k plus 1. So we are going to show that it is true for n equals to k plus 1. Note again, there are 3 steps to do, so you don't need to cram. Once you have done the base case, n equals to 1, I just add this on. They don't need you to do this. Yeah. Except if you have another condition. If the condition is for n greater than equal to 2, that means there is no 1. These are all natural number, 1, 2, 3, 4. But they can give another condition for n greater than equal to 2. That means you are not using 1 first. You are starting with 2 because your condition is for n greater than equal to 2. If your condition is for n greater than equal to 5, that means you are starting with 5. So once you've done the 5, you move to k, then you move to k plus 1. Do you get? So that's that for that. Don't worry. So show it is true for n equals to k plus 1. Now, whenever you are doing k plus 1, first write everything here. When the n was k, everything that was there on the left hand side, first write it. 3 plus 7 plus 11 plus dot 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 plus 4k minus 1. Are we together? Because assuming k is 100, now if I want to test for 101, that means I'm first going to write all the 100. Sure you understand? What's happening? This thing is blur. I'm coming. Yeah. That means I'm going to first write all the 100. So you first write everything here when your n is k. Then now plus. Now the next term, because you are doing k plus 1. Now, this how to do it. Whenever you are doing your k plus 1, you first write all the left hand side when your n was k. Then you now go back to your question. The last term there, the last term in your question. Please, this is very important part. When you are showing that your n equals to k plus 1, everything on the left hand side, when your n was k, write it out first. Plus, you now go back to the question. The last term, you now add it. What do we have in the last term? 4n minus 1. 4n, but now you are not writing it as n. What's your n? K plus 1. 4n, your n is now k plus 1 minus 1. What we have here is 4n minus 1, the last term. You had it. 4n, because your n is now k plus 1 minus 1, equals to, now our n is now k plus 1. You substitute it for here. Equals to n into 2n plus 1. So that means since our n is k plus 1, n into 2n plus 1. Do we get? So now, we are almost done. Now you can see that this guy is same thing as this guy. Are we together? And this guy is equal to this guy, meaning that we can replace this with this, because this is same thing as this and this is equal to this. That means this one is equal to this, because this is same thing as this. So since we cannot solve this, we have dot dot dot. So we can replace this guy with this. I hope you get. Maybe you should back the video and listen to that point again. So this one, everything here can change to k into 2k minus 1 plus 1 rather. No, we are replacing this with this because they are equal. How are they equal? See, they are equal here, and this is same thing as this. Some people, when they are replacing these two, they will forget that there is one left here. Yeah, so be careful. You are only replacing this. Everything here is not equal to this. It's only this one that is equal to this. So if you write this, don't forget that there is something left here. Plus 4k plus 1 minus 1 equals to k plus 1, 2k plus 1 plus 1. Are we together? So if you can prove that these two sides are equal, if you can prove it, then it is true. The statement is true for n for all natural number. Are we together? After your base case, your induction hypothesis, then your induction step. This one, when n is k plus 1, is known as induction step. Induction, like the step we take after our assumption. This is our hypothesis, our assumption. Assumption. Hypothesis is just like you are assuming. So the step you take, k plus 1, induction step after your assumption. So now, what do we do next? Here now we have, let's open the bracket. K times 2k, we have 2k square. Are we together? K times 1, we have k plus 4 times k. Some people, they will be doing 1 minus 1. This one is in bracket. First use this 4 to multiply the bracket. You can't minus this one directly. You see, this one is in bracket. 4 times k, 4k. 4 times 1, 4. Then you can now write the minus 1 because now plus 4 rather. 4 times k, 4k. 4 times 1 plus 4. We have plus a minus 1 equals to k plus 1, 2k plus 1 plus 1. So here you have 2k square. Sorry, this is plus k. K times 2k, 2k square. K times 1 plus k. 2k square plus. So you have k plus 4k. This one give you 5k. Are we together? 4 minus 1. This one give you 3. Do we get it? K times 2k, 2k square. K times 1, k. 4 times k, 4k. 4 times 4, 4 minus 1. So this is 2k square. K plus 4k, we have 5k. 4 minus 1, we have 3. Equals to this one now. This one give us k plus 1. 2 times k, 2k. 2 times 1, 2. Then we have plus 1 there. Are we together? So let's leave this side alone. Let's continue with this side. So we have k plus 1 here. We have 2k plus what? Plus 3. Are we together? 2 plus 1, 3. So this one give us k times 2k. We have 2k square. K times 3 plus 3k. 1 times 2k plus 2k. 1 times 3 plus 3. So this guy give us 2k square plus 3k plus 2k. 5k plus 3. Do we get? You can see that it's equal. Both are equal. 2k square, 5k plus 3. 2k square, 5k plus 3. Since both sides are equal, therefore, the statement is true. You write it, the statement. Therefore, the statement is true for n. Yeah, are we together? Element of natural number. So that's that for that. Now let me move to the next question. So show by mathematical induction that this statement is true for n as element of natural number. So when our base case, when n equals to 1, so you pick the first term here, 1 cube equals to, then you substitute 1 for n here. 1 square into bracket 1 plus 1 square over 4. So here you have 1 cube equals to 1 square into bracket 1 plus 1, 2 square over 4. No, 2 square is 4. So this will cancel this. So 1 cube is 1. 1 square is also 1. Therefore, you conclude it is true. It is true. for n equals to 1. Are we together? Yeah, you right. Show that it's true for n equals to 1. Now that you've shown it is true for n equals to 1. You can try to, you still see that it's true. Without wasting much of our time, let's move to our induction hypothesis. Assume, that one is assumption. Assume it is true for n equals to k. Assume it is true for n equals to k. So whenever you are doing k, I told you, you write everything on this side, everything. The k terms is a number that we don't know, so we just assume it to be a very big number, probably. So once you are just doing for k, you write everything on this side. So here now we have 1 cube plus 2 cube plus 3 cube plus dot dot dot. Whenever you are doing k, you are adding everything on the left hand side, but you will still put k wherever you see n, because now you are saying your n is k, plus k cube equals to n square, but now your n is k square into n plus 1, k plus 1 square over 4. You cannot solve this because of this dot dot dot. So after this, just move to your induction step. Your induction step, show, you are showing now, you are not assuming. Here you assume. Show that it is true for n equals to k plus 1. Show that it is true for n equals to k plus 1. Now I told you, whenever you are doing k plus 1, everything here, let me explain again. If k is 100, if k is 100, now k plus 1 will give you 101. For you to write the 101, you must first write the 100 before the 101, before the next one, which is 101, the position of 101. So if k is 90, or if k is 10, and you want to do k plus 1, that means you must first write all the 10 before the 11th. So that's why if you have n equals to k plus 1, if you want to write it out, you must first write all when n equals to k. Do you get it now? So that you not forget. 1 cube plus 2 cube plus 3 cube plus dot 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 plus k cube. Now, the next one now, we've added 1 to k. Now, the next one, assuming k is 10, if you have written all the 10. Now, k plus 1 be 11. Now, the 11th term. K is not 10, I'm just saying assuming. The 11th term, how do we write it? The next one. You now go back to your question. You check the last term. What's the last term? The last term is n cube. That's what you are adding. You are adding n cube here. Whenever you are doing k plus 1, after you've written everything when n is k on the left hand side, you now add the last term in the question again. But now that you want to add the n cube, you now write n. Now your n is k plus 1. Your n cube will now be k plus 1 cube equals to, now what's the right hand side? N square. But now your n is k plus 1. When your n is k, n square, k square, n plus 1 square, k plus 1 square over 4 over 4. But now your n is k plus 1. So n square, here you have k plus 1 square, n plus 1, k plus 1 plus 1. Our n is k plus 1 square over what? Over 4. Are we together? So, this guy is same thing as this guy. Can we see that? And this guy is equal to this guy. Since both are equal and both are the same, that means you can replace this with this. So since this one we can't solve it, we have dot dot dot, so we can replace it with this, since it's same thing as this and this is equal to this. So everything here can change to k square, k plus 1 square over 4. Yeah, this guy. Plus, I told you, it is only this you are replacing, because it is only this that is same thing as this. Some people used to do mistake. Once they put this to replace this, they will forget that something is left here. It is only this that is same as this, and this is equal to this. So we are replacing this with this. Don't forget what is left here. K plus 1 cube equals to k plus 1 square, k plus 1 plus 1, you have 2 square over 4. Are we together? So what's the next thing we want to do? Now let's find the LCM here. The LCM is 4. Are we together? The LCM is what? Is 4. I don't want to touch the right hand side again. Let's just keep this guy. Let's keep it there for now. Let's deal with this one. So if you are writing it again, you'll be wasting your time. Just keep it. Focus. You can focus. Once you see that one side is like perfect, you can focus on the other side and make it perfect. So if at the end of the day you realize they are still not equal, then maybe you can be expanding your bracket. But this one seems perfect now. I don't want to expand bracket yet. Let me leave this one alone. Let's focus on the left. So now my LCM is 4, abi? 4 in 4, 1. 1 times this. 4 in 4, 1. 1 times this. I still have the same thing. K square. K plus 1 square plus this over 1. 1 in 4, 4. 4 times this, I will have 4 into K plus 1 cube. Now, if we check these two, what is common to both of them? This one have K plus 1, this one have K plus 1. K plus 1 is common to both of them, but I can still improve further by saying K plus 1 square is common to both of them. Because here I'm having K plus 1 square. This one is skip. I can remove K plus 1 square from it. So if you bring out K plus 1 square from both sides, I want to factor out K plus 1 square. Open bracket. What will remain here? If I bring out K plus 1, I will have K square left here, right? Plus, what will be left here? I will have 4 into K plus 1. Now, if you do K plus 1 square times K square, you have this. K plus 1 square times 4K plus 1, you have 4K plus 1 cube. Because K plus 1 square times K plus 1 will give you K plus 1 cube. This 4 over 4. Are we together? So here I'm having K plus 1 square, open bracket, K square plus 4 times K, 4K, 4 times 1 plus 4. Shine your eyes here. Don't say 4K plus 1. You are using the 4 to multiply the 2. They are in bracket. 4 times K, 4K, 4 times 1, 4 over everything over 4. Are we together? So now what do? You have K plus 1 square. Now, this one now, we can factorize it. You can factorize it. I don't want to be doing factorization step. This is a quadratic equation. This is a quadratic equation. What are the two things you can multiply that will give you 4? If you add them, it will give you 4 again. Plus 4 if you multiply them. If you add them, it will give you plus 4K. No factorization. It's just 2 and 2. So I can change it to K plus 2 and K plus 2. See, this is K times K, K square. K times 2, 2K. 2 times K, 2K. 2K plus that 2K, 4K. 2 times 2, 4. If you expand this, you will get this guy back over 4. So this one is same thing as K plus 1 square. If you have A times A, that will give you A square. So K plus 2 times K plus 2 is same thing as K plus 2 square over 4. You can see that here I'm having K plus 1 square multiplied by K plus 2 square over 4. You can see the right hand side. K, so both sides, they are equal. You can see K plus 1 square, K plus 2 square over 4. Both sides, they are equal. So now you can conclude that it is true. It is true. The statement is true for n as element of natural number. Do we understand? Now the last question. The last question is this guy. Now, here now they did not write n element of natural number. They write n greater than equal to 1. This one is still the same thing as natural number because natural number is 1, 2, 3, 4. So if your n is greater than equal to 1, that means you are still starting from 1. 1, 2, 3, 4. But assuming they put 2 here, that means they have removed 1. You can only start from 2. Just be checking your condition before you proceed. Assuming I'm having 2 here, the first base case I will do is show that it's true for n equals to 2 because my condition is n greater than equal to 2. But here I can still follow that one with natural number because they put 1 here for n greater than equal to 1. So please always check your condition. It's not every time that you'll be starting from n equals to 1. It depends on your condition. But here I can still start with n equals to 1 because the condition is n greater than equal to 1. So now, for n equals to 1, show that it's true, that the statement is true for n equals to 1. So please, in mathematical induction, whenever you see dot, this is not 1.3. Whenever you see 1 over, it's not decimal, it's multiplication. We call it dot product. I'm not even speaking about vector, like dot multiplication, something like that. 2.4 means 2 times 4. Particularly this topic is not decimal, just take note of that. So this one is same thing as 1 over 3, this one is same thing as 1 over 8. What's happening to this camera? I'm sorry. So here, show for any customer, I'm going to pick the first term alone here. It's 3, I told you, 1 times 3 equals to, here I'm having 3 over 4 minus 2, no, my n is 1 now, plus 3 over 2 n plus 1, 1 plus 1 into n plus 2, 1 plus 2. So here, let me leave that 1 over 3 alone, equals to 3 over 4 minus 2 times 1, 2 plus 3. That's 5 over 1 plus 1, 2 times 2. That's 4, right? 1 plus 2, 3. So this guy gave me 3 over 4 minus 5 over 12. Yeah, minus 5 over 12. What's the S here? The SM is 12, right? 4 in 12, 3. 3 times 3, 9. Minus 12 in 12, 1. 1 times 5, 5. 9 minus 5, 4 over 12. 4 here, 1. 4 here, 3. You can see 1 over 3 equals to 1 over 3. Therefore, the statement is true for n equals to 1. Therefore, it is true for n equals to 1. Are we together? Now, there's no time to be doing n equals to 2, but if you want to have fun, if you are doing exam, once you've done one of the base case, just move to your induction hypothesis. There's no time for testing or for having fun, but you can do it for fun's sake, or for confirmation sake. Now, our induction hypothesis, assuming, that one is an assumption. Assume it is true for n equals to k. Assume it is true for n equals to k. So whenever you are doing n equals to k, you are writing everything here. You are writing everything. I said it now, times with that number. So here you are having 1 over 3 plus 1 over 2 times 4. That's 8 plus dot 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 plus 1 over. Now, n, but now my n is k. K plus 2. Are we together? Equals to 3 over 4 minus 2n plus 3, 2k plus 3 over 2 into n, k plus 1, n plus 2, k plus 2. Now that's my assumption, induction hypothesis. Now my induction step. If it is true for n equals to k, show that it is true. It is true for n equals to k plus 1. Once you have shown it, you are good to go. Now I told you when you are doing n equals to k plus 1, first write everything on the left hand side when n is k, and I've told you the reason. So this one is 1 over 3 plus 1 over 8 plus dot 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 plus 1 over k into k plus 2 plus, now don't write is equal to yet, plus, because you are doing k plus 1. So you've written the k. Now what's the next term? If k is 100, k plus 1 will be 101. So I've written the 100 now. I want to write the 101th term. Just assuming that k is 100, I'm just fan assumption, because you don't know what k is. So I've written the k. It now remains the k plus 1th term, the next term after k. If I'm doing k, if I'm now doing k plus 1, that k plus 1 means the next term after k. So that means all of the terms from 1 till k plus 1. Now, what I've written here is all of those terms from 1 to k now remain the term for k plus 1, the next term. Like, don't be confused. Maybe you should back it the way I explained it earlier. Maybe that one will help you. Assuming my k is 10, k plus 1 will now be 11. So if I want to write k plus 1 on the left hand side, I'm going to write the first 11th term. So the k now represents the first 10th term. Now it will now remain the 11th position. Are we together? Just an assumption. That's just like explanation, though my k is not 10. But it can be any natural number, sha. Now, I've written the k. Now, the k plus 1, I told you will add the last term. The last term. Once you have written the k part plus the last term, what's your last term? 1 over n into n plus 2. plus 1 over n. But what's your n now? K plus 1. 1 over n, my n is k plus 1, into n plus 2. N plus 2, k plus 1 plus 2. Do you get? Equals to 3 over 4 minus 2n plus 3. But my n is k plus 1. 2k plus 1 plus 3 over 2 into n plus 1, k plus 1 plus 1, because my n is k plus 1, into n plus 2, k plus 1 plus 2. My n is k plus 1. Now, you can see that this guy is same thing as this guy, and this guy is equal to this guy. That means wherever we see this, we can replace it with this. So this one gives us 3 over 4 minus 2k plus 3 over 2k plus 1, k plus 2, plus, don't forget, it's only this one you are replacing. There, we still have something left here, plus 1 over k plus 1, k plus 3 is equal to 3 over 4 minus, let's multiply, 2 times k, 2k, abi? 2 times 1, 2 plus 3, that's 5, over 2 into k plus 1 plus 1, that's k plus 2, k plus 1 plus 2, that's k plus 3. Are we together? So now, let's move on. What do we do here? Now, both of those sides have 3 over 4. Sure you get? So let's leave 3 over 4 for now. Since both of them are having 3 over 4, let's see if this 2 is equal to this 1. Leave 3 over 4. Both of them have 3 over 4. Let's keep the 3 over 4. Now let's check if this one is equal to this one. Now, if these two are equal, then we can add 3 over 4 at the end of the day. Let's just focus on those two. Are we together? So let's find, what's the LCM here? The LCM there is 2 into k plus 1, k plus 2, k plus 3. No, we have 2. We have k plus 1. We have k plus 2. We have k plus 3. The LCM of these two is this guy. Even though we have 2k plus 1, you don't have to write the 2. Just write the 1. The 1 is okay for them. Sure you get. So this in this, this in this, it remains this, right? This guy, 2k plus 1, k plus 2, and this, it will remain this, because this will cancel out this, it will remain this. So this times this, sure you get. You now have, don't forget the minus, it's only 3 over 4 we are leaving. You now have this times this, you now have 2k plus 3, then k plus 3, plus this in this k plus 1, k plus 3, k plus 1, k plus 3, it will remain 2 and k plus 2, right? This in this, it remain 2 and k plus 2 times 1, and we have 2k plus 2. Let's leave this side alone. Let this one sit down there. Let's focus on this one. At the end of the day, if we can make this guy equal to this guy, then we are good to go. Now let's continue. Let's open the bracket. Are we together? So this guy gives us minus 2k times k, 2k square. Are we together? 2k times k, that's 2k square. Should that be correct? Yeah. 2k square. 2k times 3, that's plus 6k. 3 times k plus 3k. 3 times 3 plus 9. Plus 2 times k. You don't even need 2k. 2 times 2 plus 4. Over, in fact, since I've expanded, I don't even need this bracket again. Sorry for that. Over 2 into k plus 1, k plus 2, k plus 3. So now let me use, okay, I still have minus. The bracket is necessary. Let me use this minus to open the bracket. Minus times this, I have minus 2k square. Minus 6k plus 3k, that's 9k. Times minus, minus 9k minus times 9 minus 9. Then here I'm having plus 2k plus 4 over 2 into k plus 1, k plus 2, k plus 3. Are we together? So this guy give me minus 2k square minus 9k plus 2k. I will have minus 7k minus 9 plus 4. I will have minus 5 over 2k plus 1, k plus 2, k plus 3. So I can let's factorize this numerator. Don't forget, I left 3 over 4 alone. Let them stay. It is only this guy I'm breaking down. I want to see, after breaking it down, if it can be equal to this. That's what we are dealing with. Are we together? So now, you are going to, we know we are an upcoming fresher. We know how to do factorization. The coefficient of k square here, you multiply it by c. So minus 2 times minus 10, that's plus 10. So the two factor you are looking for is two things that you will multiply that will give you plus 10. If you add them, it will give you minus 7. That's what? Minus 5 and minus 2 are. So this guy give you minus 2k square minus 2k minus 5k minus 5. Are we together? See, minus 2k minus 5k minus 7k minus 2 times minus 5, it will give you plus 10. Don't forget how we get plus 10 here. You are going to multiply this by the coefficient of k square, factorization. If you don't know factorization, go and learn it and come back to this point. Sure you understand. So here I'll be having 2 into k plus 1, k plus 2, k plus 3. So now this guy give me, I'm not writing the right hand side though. I'm not writing this, so it's just this I want to write here again. So this guy give me, what is common to these two? What is common to both of them? That should be let me just bring out, that should be, let me bring out minus 2k. Here I will now be having k plus 1. Are we together? Minus 2k times k minus 2k square minus 2k times 1 minus 2k. So here, these two, minus 5 is common to both of them. So I would still have k plus 1. Are we together? No, minus 5 times k minus 5k minus 5 times 1 minus 5 over 2 into k plus 1, k plus 2, k plus 3. Are we together? So now at the end of the day, here, what is common to both of them? You know how to do factorization. Just these two are the same. Just pick one. What is common to both of them? K plus 1. Oh yeah, bring out k plus 1. What will be left here? Minus 2k, abi? Minus 2k. What will be left here? Minus 5 over 2 into k plus 1, k plus 2, then k plus 3. So you can see that k plus 1 will cancel k plus 1. Are we together? K plus 1 will cancel k plus 1. So what will be left there? I'll be having minus 2k minus 5, but I can bring out minus from both. So here will remain 2k plus 5. No, here is minus 2k minus 5. Minus times 2k minus 2k. Minus times plus 5 minus 5. So I bring out minus. I factorize out minus. Over, what do we have left at the denominator? I have 2. Then I have k plus 2. Then what? K plus 3. So we can see this is what I get now. So now let me add the 3 over 4. Now, the final answer now. Now the 3 over 4 here. So I'm having 3 over 4. Are we together? Don't forget, I've used this minus. So it's what? Minus. No, I've turned everything here. Those are the things we did. Those are the things we did. And we arrive at this point. Minus 2k plus 5 over 2 into k plus 2, k plus 3. Let's check if it's equal to the right hand side. What do we have? This is what we translate to this. Is equal to, are they equal? 3 over 4, 3 over 4. minus 2k plus 5. This one should be in bracket. Yeah, take note of that. Minus 2k plus 5. Are we together? 2k plus 5 over 2 into k plus 2k plus 3. 2 into k plus 2k plus 3. So both sides they are equal. Therefore, the statement is true. Therefore, therefore, the statement is true for n greater than equal to 1. Don't put, just follow what they write. This one is still same thing as this. Are we together? Because natural number is same thing as 1, 2, 3, 4, 5, 6. And anything greater than equal to 1, that's 1, 2, 3, 4, 5, 6 till infinity. Shall you get? So therefore, it's true for n greater than equal to 1. So that's that for that. Please just go back and listen very carefully. Thank you very much. Thanks for watching. Please like and subscribe. And also share to your friends.